welcome to the new episode of the Hands-on Optimization Masterclass. I am Cristina Radu, and we have here with us Felipe Brandão. And let's get started. We are going to talk today about the main topic is lot size and incremental lot size. And Felipe also added the scenario functionality. But we will start by checking the homework. So in the previous session, we talked about transfers. So now we also added the reports where you can validate and visualize the stock movements in the network. Then how to add targets. So target stock by the same is techniques you can use for max stock, cycle stock, and layered penalties. And here you can try layered targets. So what happens if you put different penalties for different layers of the targets and also for the storage. So now I will ask Felipe to show you the homework directly in the app because we added a lot of options and yeah, so it helps you become familiar with what has been developed. So Felipe, if you want to share the screen.
So can you see my screen? So here we have the app for homework 3. And here I have the checkbox for show complete model enabled so that you can see the solutions. So in this app, we have transfers, target stocks, and storage capacity. Here we have the transfers. So we have transfers lanes. So for certain products between pairs of locations, the variable
So
transfer.
this is the data. This is what comes in from
Yes.
the user.
Yeah. So this is from the data. So you define which lanes exist between different locations for transferring different products. Then there is this variable that is the amount of a certain product that is being transferred between two locations. And then there are these two defined variables, which are not true variables. They are essentially just a simple way to express this. So essentially aggregating everything that is going into in a certain product, for a certain product at a certain location, in a certain time period, the total amount being transferred in, and the same for the total amount being transferred out. So that in the material balance, so before we already had starting inventory minus met demand plus production. So now other than production, you can also have transfers in, and you can also be have some products leaving, so some transfers out. And that is equal to ending inventory. And this is exercise 1. Then exercise 2, the target stocks. So target stock is, so this is input data. So you decide how much you want to be the target stock. It needs to be equal to ending inventory plus these two auxiliary variables that allow you to be above or below the target stock. So the two strictly positive variables. And then they are going to be penalized in the objectives. So I can scroll to the objective just to show. So here we have a penalty for the amount being above target and another penalty for the amount below the target. And with this, you can have some flexibility instead in terms of being close to the targets, but not strictly be meeting them.
And I see you added the penalty also for the transfer. So let's say that you also need to add a penalty in the objective function for the transfers. Otherwise, the solver thinks that can transfer as much as it wants. So it just takes stock and moves it through the network. So you see it moved from one location to another. If you put a penalty, it only does the ones that are needed to meet the demand.
Yeah, so that is this last penalty here.
Yeah.
And then other than this, there was just storage capacity. So at every location, at every time period, we have this data. In this case, it's just max capacity across all products. So for all products in that location, the total ending inventory needs to be less than the capacity at that location. This could also be depending on the product and also on the time period. In this case, it's just a global limit for each location. And other than this, there are the layered targets, which is just a small change in the objective.
And the data, you need the new data
Yeah,
basically
yes.
to.
Yes, so there are like more control parameters because in layer targets, uh, what happens? So instead of having just a penalty time above target or a penalty times below target, now we can have, if the above target is less than 5, then we can have just above target, uh, the amount above target times the penalty. So just like we had before. But if it is above 5, then we want just a flat penalty, let's say 10 times the above penalty. And the same for below target. So instead of having just below target times below target penalty, we have this condition. If below target is less than 5, so we are just a little below, then is this penalty. Otherwise, is this other penalty that is constant. So you just make this small change in the objective, and that's it. You have the layer targets implemented.
Yeah, so this gives you the opportunity to put a higher penalty when you go too much above and too much below. So that's just to make it clear. So for example, Felipe put here 10 times above target penalty, but you can put 100, 1,000. So just to make sure the solver doesn't go there. But if it goes there, it means it's necessary. So then it pays the penalty. Okay, thank you, Felipe. And now let's go to the lot size. So here we are presenting two ways of approaching the lot size. So one is using the big M method, where you introduce a binary. And then the other one is lot size with logic, which is something you can do in AMPL or other languages, but that's not always possible. So the big M works for in any software and any language. The logic bit, it's specific to certain languages like AMPL, which enable this. So it's like a functionality that is enabled. And talking about the big M, basically you introduce a binary which tells you if you start or not a lot size. So do you produce or not the lot size? And then you also use a slack variable, which tells you that you go above the lot size. So when you only have lot size, it means that if your lot size is 100, you can produce 100 or 101 or 140 and so on, everything about 100. If you can only produce 90, there is no lot size. So the production becomes 0, basically. So the production is either 0 or above 100. And these are the equations. So the production needs to be equal to the lot size, yes or no. That's the binary and the above in lot size. And then you need extra constraints to basically yeah, to flip the binary. So the production should be less than a big M times the binary, and bigger than the lot size times the binary. So if the binary is 0, the production is forced to be 0 because of those two constraints. And if the binary is 1, then the production needs to be bigger than the minimum lot size, which is an input from the data, and smaller than this big M. And big M is a number which should be big enough than anything that you might produce. And I will let Philippe explain you the logic in the app, but let's go to the next slide first. So what happens if you also have incremental lot size? This means your minimum lot size is 100, but you want to produce in increments of 7. So you can produce 100, 107, 114, 121, and so on. So then you need to introduce an integer variable. So you have the binary which tells you if you start the lot size, basically if you are going to, if you have enough resources, capacity, and so on to produce the 100. and then it needs to be in increments of 7, and you control that with the integer. And then you have a similar constraints to keep the production under control. So if the binary is 0, the production needs to be 0. And if the production is bigger than 0, then it needs to be bigger than the minimum lot size. And then there is a similar way to do it in AMPL, just using logic. So basically, what I just explained, you write it as it shows on the screen, and then the language picks it up and knows what to do with it. So if you want to show it in the app.
Yeah. So let's go again into the app. So homework 4. So in here we are giving the many options for you to see minimal lot size, minimal incremental, and also both options in terms of how to write it. And also here you have checkboxes where you can simplify the model, essentially removing what we learned in homework 2 and homework 3. But for the model to really produce results that make sense, it's important to have this enabled, because for instance, if we don't have transfers, you are going to be missing demand in the market because you are not able to produce there. So it is important to keep them here, even though the model is going to have the full complexity with everything, and means that I need to scroll down more to get the lot size. I'm going to start with just min lot sizing with logic. So I need to scroll down. Target storage capacity, so the previous homework, and that's it. So minimum lot sizing with logic. The only thing you need, you have a parameter that is going to control the minimum lot size. And then in Ample, you can just write it like this. So production is equal to 0 or production greater or equal than min lot size. Then behind the scenes, this can be turned into big M's or better things. So one thing that often people imagine that you always need big M is not always big M. Like big M can be quite bad numerically. And there are alternatives that the solvers provide, like indicators, special ordered sets that can be more powerful. And when that is available, we use it. So you get the best performance on the different solvers using what they have available. So this is just with logic, and just to show you how it becomes with big M. Let's go down again.
So just to say here, the idea is with the big M, it's if possible to avoid it because it's you introduce binary, so integer, so the performance drops immediately, very fast. Plus also the results, sometimes they become a little bit hard to interpret. So if we can avoid it, good. If not, yeah, it works, but so you know that it will impact the performance.
Yeah, because BigM, there is a very particular thing about BigM is that often people imagine that BigM can just be one very large number, and this a good BigM needs to be as small as it can be. For instance, in this case, the BigM that I'm using is just really summing the total demand across all time periods, because essentially without knowing much more about the data, in one time period you could be producing for the entire horizon. So it could really be the maximum production. But if you have better bounds, you should introduce them also on the variables, because by doing that also allows the solvers to eventually improve your BigM, even though ideally you should already be avoiding it from the start, because it can get problematic very easily, especially when you are solving very large problems. It can cause a lot of trouble. But it's something that if you are limited to solvers that don't have indicators, then that's what you end up using. Here you have it. You have that variable for the above minimum lot size, binary variable whether or not to produce. Produce is going to be 1 if there is any production. So if production is different from 0, then so if produce is 1, then production must be at least min lot size. If produce is 0, production must be 0. If produce is 1, production can go up to max production, which is the big M that we have here. And also we have this condition that is production is equal to produce times minimum lot size plus this variable that allows you to go above it. And as you can see, it's already a lot more complicated than just be able to write logic, and also more error prone. Now, minimum price incremental and with logic, it is going to again be very simple. Incremental lot size. Okay. So production either 0 or production is equal to minimum lot size plus increment lot size times ls increments. So this is a variable, an integer variable that is going to be how many increments above the minimum lot size you want to have there. So 0 or more increments of, in this case, defaulting to 5. So you either produce 10 or 15, 20, 25, and so on. And this is using logic. And the same with big M. It's going to be very similar to the previous one. The main difference is here that now we also need to consider the incremental lot size times increments. But other than that is just like before.
Okay.
And
Yes.
yeah.
I know. I wanted to say that we forgot to show the target report. So if you finished, we can do that and then move to the scenarios.
Yes, I forgot the target report, and I forgot the transfers, which is something that we have transfers here. I can just come down here and
So first, the transfers are in this report, the material balance overview. So here you have like the full picture of what happens in your network, and you either have the aggregation or you can put filters by location, by product, and so on. So you see how the stock is moving either visually like this or with the planning view, and then the reports for the transfers.
yeah, and that is the report here on the transfer, so that you can see, in this case, it's aggregated or for a certain product where it is moving from. And this is also where you can see why if we disable homework 3, we will be missing a lot of demand because market really needs to receive from others, from bakery, because they are not producing there. And that was introduced in homework 2. So the resources and so on. Okay, and yeah, so this is in terms of reports. Now, in terms of scenarios, there is one thing here in the app is that after you see the solution, so after you pick a solver and you solve a problem, here you have the opportunity to now save the scenario, so picking a name and so on. Let me see if I have some saved. Yeah, I already have some saved, which is what I'm running now. So minimal plus incremental with big M. So min plus mental sizing with big M. Save the scenario. Okay, and now that I saved the scenario, it is here, and I can either visualize just individual scenario, essentially updating the reports to show that scenario, or I can pick two and compare. So for instance, minimal lot sizing with logic compared against minimal lot sizing with big M. And as expected, like the results are the same, they are modeling the same thing. And I can also show the difference, for instance, when you move to incremental. So for instance, here in terms of production, we have like 195, 140, 108. So we just need to be above the minimum to be able to produce. But when you have minimum plus incremental, we have the minimum of 10 and then multiples of 5. And then you can see here like production 190, 145, 100, 115, and so on. So you can see that the lot sizing is having impact in terms of how much we produce. And you can see the small differences here in visually as well.
Yes,
Yeah.
it looks great, the scenario functionality. And the way you can use it, so for example, you can change capacities, right? So let's say you produce in one bakery for 5 days, in the other for 7 days. And then you can come and compare scenarios, or you can increase demand by 10% or decrease by 10% in a certain location. So these are examples of what planners want to see in a scenario. What you can also do is play with the penalties in the objective function, because now you have targets. So when you put a higher penalty, lower penalty, you see that the results change. Same with the storage constraints. What else did we add there? Yeah,
Right.
transfers also. What you can do is like in one scenario, you can block some lanes or open some lanes and see how are the materials moving through the market. So the scenario functionality is very powerful to also understand how a solver works. So to see this correlation between the input and the output, because if you change the input, you see the output and you understand how everything comes together in the solver.
Yeah, and I'm just going to show you like a small use case when playing with penalties, for instance. So below target penalty, let's imagine that we reduce it to 1, and let's see what happens. Mm, no. Okay, and we have this. And you can see here, the target stocks now not being met, the penalty is too small. So it is also a good way for debugging too, because since we have all these soft penalties in the objective, sometimes constraints might be ignored.
Yeah, so you see the difference in the ending inventory. In
Yes.
scenario A, ending inventory is quite big, 149, 183 in the planning view, whereas in the scenario B, the ending inventory is like 930 and so on, like down in the planning view there. The
Yeah,
line
yeah,
is the ending inventory. So yeah, it's very clear. It doesn't take into account this penalty for the target stocks.
yeah. Yeah, and also to show the importance of these penalties, like it's important to be careful and really validate well, so that you might, even though you might have everything in your model, if you did not pick right the penalties and you are using this approach to essentially provide more flexibility to ensure that you are still satisfying the constraints and not having them ignored completely. Okay, and
Yes.
you want to switch back to the slides or?
Yes, so
Yeah.
the lesson for today is finished. You just need to go in the app and practice, because you saw a lot of options, a big M, the logical, and so on. So it's just a matter of practice. Now you have what you need to understand how it works, and the scenarios in which you can compare what happens between when you change a parameter or a penalty or even the input. And for the next class, we are going to talk about campaign optimization. So we are going to define what is campaign planning, campaign optimization, and then I will give you 10 questions that you should ask when the client says, well, I want to have campaign planning, because there are different ways to approach this problem. And some of them are, let's say, less performant, less user friendly, and so on. So by having those questions, you can see which method is best to apply. And I'm mentioning here what are the map methods. So one is the MIP, so using integers, which is the most costly in terms of performance. Then you can use an LP plus a heuristic, and this is very fast and very efficient. And there is another way that the clients can create a product wheel. So then you know the sequence in which you want to produce the products, and then you use the exclusion calendar to enforce this in the solver. And quickly, we're going to mention also if you need to model the maximum number of changeovers, how can you do that, especially in a context when you have campaign planning. So this is it from today. Thank you for joining, and we will see you next time. For any questions or remarks or suggestion, just let us know. Thank you, and we'll see you next time.
Thank you.